Hey, take a look around you for a second. That desk you're at, the air you're breathing, even the light coming from your screen. What if I told you all of it, absolutely everything, is made of the same basic stuff? Well, in this explainer, we're going to dive deep into the invisible world of atoms, the tiny building blocks that make up our entire reality.
So, let's kick things off with a pretty big question. What's the one thing that connects you, the air in this room, and a star billions of miles away? The answer, it turns out, is the key to, well, understanding pretty much everything. And that's exactly what we're going to unpack today.
You got it. That common thread is something we call matter. And we use that word all the time, but what does it really mean from a scientific point of view?
It's actually pretty simple when you break it down. Matter is just anything that has mass. You know, the amount of stuff in it and takes up space. So your phone, your coffee, the air you just breathed out, it's all matter. And every single bit of it is made from these countless tiny individual particles.
Right. And how those little particles are behaving is what gives us the different states of matter. Think about it like this. In a solid, the particles are like a perfectly seated audience in a theater. They're packed in tight, orderly, and not moving around much. In a liquid, it's more like a busy party. The particles are still close, but they're mingling and sliding past each other. And a gas? That's like people spread out in a giant open field, just zipping around with tons of energy. Totally free.
Okay, so we know matter is made of particles. But what exactly are these particles? For a long time, that was a huge mystery. So now, we're going to take a little trip back in time to see how scientists finally uncovered the invisible blueprint for everything, the atom. You know, our understanding of the atom didn't just pop into existence. Nope, it was pieced together over more than 100 years by some seriously brilliant people. Each new discovery built on the last one, kind of like solving a giant puzzle, slowly revealing what the atom actually looked like.
Our story really kicks off back in 1803 with a guy named John Dalton. His idea was that an atom was just a tiny, solid sphere, kind of like a miniature billiard ball. For him, it was the smallest thing possible, and you absolutely couldn't break it down any further.
But then 1897 happens, and J.J. Thomson discovers the electron. This was a game changer. It proved the atom wasn't a solid ball after all. His new model was something people called the plum pudding model, basically a big ball of positive stuff with these little negative electrons dotted throughout, like chocolate chips in a cookie.
Just over a decade later, Ernest Rutherford completely flipped the script again. His incredible experiments showed that all the positive charge was actually crammed into a super tiny dense spot right in the middle, the nucleus. And this led to a wild realization: the atom is mostly empty space.
Next up was Niels Bohr, who added a crucial detail to Rutherford's model. He figured out that electrons weren't just buzzing around randomly. Instead, they were stuck in specific orbits or shells around the nucleus, kind of like planets orbiting the sun on fixed paths. It brought a new sense of order to the whole thing. And the final major piece of this puzzle clicks into place in 1932, thanks to James Chadwick. He discovered the neutron, a particle with no charge at all that hangs out in the nucleus with the positive protons. And with that, our basic, modern picture of the atom was finally complete.
So now we have the ingredients: protons, neutrons, and electrons. But how do we tell one kind of atom from another? Well, it turns out every single atom has its own unique identity card, and reading it is all about knowing two simple numbers.
It really all boils down to these two numbers. First, you've got the proton number. This is the big one. It's just the number of protons, and it is what defines the element. Every single carbon atom in the universe has 6 protons. Every oxygen atom has 8. No exceptions. That number is its identity. Then you have the nucleon number, which is just the protons and neutrons added together. That tells you about the atom's weight. And scientists have this really neat shorthand for writing it all down. X is just the symbol for the element, like C for carbon. The number on top is the nucleon number, the total weight. And the number on the bottom is that all-important proton number, the one that tells you exactly what you're looking at.
All right, so if the number of protons tells you what an element is, you'd probably think that all atoms of, say, carbon are identical clones, right? Well, this is where nature throws us a really cool curveball. Let me introduce you to isotopes.
So, what is an isotope? It's basically a different version of the same element. All isotopes of an element have the exact same number of protons. They have to, otherwise they'd be a different element altogether, but they have a different number of neutrons. This means they act the same chemically, but they weigh different amounts. Some are a little heavier, some are a little lighter.
Let's take chlorine. It's a perfect example. Both of these atoms here are chlorine. Why? Because they both have 17 protons. That's chlorine's ID number. But if you look closer, chlorine-35 has 18 neutrons, giving it a total mass of 35. Its heavier sibling, chlorine-37, has 2 extra neutrons, 20 of them, giving it a mass of 37. Same element, just different weights.
Okay, at this point you might be thinking, this is all cool science, but why should I care? What does this have to do with my life? Well, it turns out that understanding atoms, and especially their isotopes, has totally transformed our world in some really amazing and practical ways.
And there is no better example of this than in medicine. I mean, this atomic know-how is literally saving lives every single day. You see, certain isotopes are radioactive, and we've learned how to harness that energy for incredible things. Cobalt-60 is used in radiotherapy to zero in on and destroy cancer cells. Doctors use iodine-131 to check on the thyroid gland. And things like phosphorus-32 can help them find exactly where tumors are located. It's amazing stuff.
And the applications don't stop there, not by a long shot. This knowledge helps us unlock secrets from the distant past and even helps us build a safer future.
Ever wonder how scientists know how old a dinosaur bone is? That's carbon-14 at work, acting like a perfect natural clock. Want to figure out how to grow more food for a hungry world? Phosphorus-32 helps us design better fertilizers. And how about keeping our cities safe? An isotope like sodium-24 can find a tiny, dangerous leak in a pipe that's buried deep underground.
So there you have it. From the air we breathe to the tech that saves our lives, these tiny invisible particles are the foundation of, well, everything. They are literally the blueprint of our world, which really just leaves one last exciting question to think about. What are we going to build with them next?